All right. We're going to start with synchrotron emission. And, we've already spoken about that before. Synchrotron emission is just the emission from highly relativistic charges, which are moving in a magnetic field. So you know that the dynamics of a charge in a magnetic field is to go in circles, or in the general case, in the form of a helix. And when the charge is highly relativistic, all the relativistic effects you learned about, like aberration, time dilation, these things, and the Doppler shift, these things become important. And so we have a special name for that kind of emission, and it's called synchrotron emission. And we're going to basically learn a few things about synchrotron emission. What I want to do in this case is I want to go through the hard formal derivation, which has a lot of algebra in the lecture videos. And I want to do the more intuitive derivation in class. And actually, you will do the derivation. I'll just give you a set of problems such that in the end, you'll get to the answer for, let's say, the emissivity of a synchrotron fluid or something like that. But I want to do the more rigorous algebraic derivation in this video. And so we basically are going to go back to first principles here. We're going to say that we have a charge which is going in a helical trajectory, and we're going to try to find this quantity here, the amount of energy emitted per unit frequency per unit solid angle from this charge. That's what we're going to try to figure out. Now, I'll come to the geometry in a bit. This is the geometry of the problem, but just to set up what we're trying to derive here, that quantity, if you go back to your notes, you would see that because it's a spectral domain quantity, it's related to the Fourier transform of the electric field. And so if you take the Fourier transform of the electric field and then, try to find the Poynting flux, you can go back to your notes from chapter 3, and we basically showed this. So this is just the Fourier transform of the electric field, and notice that the electric field has to be calculated at the retarded time. And the C here comes from the Poynting theorem, right? So we're trying to find the Poynting flux. And so we basically have to evaluate this quantity here for any given emission mechanism. This is true. So you can actually write down the retarded electric field. We actually derived this from the retarded potentials. And you basically get this expression. I think this should be familiar to you. N cross N minus beta cross beta dot times this is kappa. So kappa was 1 minus n dot beta, where n was the unit vector pointing from the retarded position of the particle to the observer, and beta was the speed of the particle divided by the speed of light. So that's that factor kappa, which was also the Jacobian, if you remember, between t and t prime, where t prime was the retarded time and t was the coordinate time for the observer. Okay, so we basically have to take the Fourier transform of that, and that's what we really want to evaluate in this case. And so I want to make a few simplifications here, which is true in general, and then we would come back to the specific problem of synchrotron emission. So if you want to evaluate this in general, there's a nice trick which you should know about. So it comes in 2 steps. So first step is to take your observer coordinate time, and then change of variables to the retarded time. And because that makes this integral simpler, because this quantity here is calculated at the retarded time t prime. And so you have that relationship between t prime and t. And all of this should bring back some memories from chapter 3, where we did all of this. And we showed that the Jacobian between those two was kappa, basically, right? So you can actually get rid of one factor of kappa and then replace dt with dt prime. Okay, so I've done that here. So you can pause the video and make sure that I haven't made any serious mistakes. And so what I've done is I've replaced all of the t's with t primes. I've just cast the integral in terms of t prime. And of course, the exponent becomes a little more complicated now, obviously, because, I've basically substituted for t. And you get something like this. So I have kappa to the power minus 2 instead of minus 3 because, the Jacobian took care of one of the kappas. Now there's the second trick here is a nice little trick to actually evaluate this integral. And it turns out that you can do this integration by parts. And the two functions which is the integral product of is the exponent here, and the other one is this complicated geometric function with this n cross n minus beta cross beta dot times kappa to the power minus 2. Now it turns out that this function is actually a perfect derivative, which makes the integration by parts very easy. So it turns out that that whole factor here is just the derivative with respect to t prime of n cross beta times kappa inverse. Okay, so it turns out that this is a perfect derivative, which means now you have an integral of the form f dash of x times g of x, and you know how to integrate that by parts. You take g of x outside, so you get g of x times f of x as the first term, and so on. So you know how to do that integration by parts. So I've done that here. Again, you can pause the video and check the algebra. And the upshot is you basically get to a quantity that looks like this. So you get what you're interested in, the amount of energy per unit, per unit frequency, per unit solid angle, and you basically get this complicated integral is now cast in a much simplified form, and it just becomes an integral of this simpler function. Sorry, I'm missing an integral sign here. There should be an integral. So it just becomes a simple integral of this function, which is n cross beta. So that's much simpler function than what we had before, times the exponential, which remains the same, and that's basically the effect of retardation inside the exponent. Okay, so all of this is true. It's exactly true for any emission mechanism. And so now we're going to go to the particular case of synchrotron emission, and we're just going to try to calculate n cross beta and then this factor here in the exponent, right? So any emission mechanism you have, you can basically plug in, given the dynamics of the charge, you can plug in these quantities, and then you can back out the Poynting flux from that. Okay, so now we're going to put in these values for the particular case of synchrotron emission. So let's go back to the geometry. So I told you, you've already seen that a charged particle in an external magnetic field goes in along a helix, right? And so we need to choose coordinates which are going to make our life simple here. And so I'm going to choose coordinates where at the retarded time, when you're actually calculating that quantity, I'm going to assume that the particle is moving in the xy plane. Okay, so it has a curved trajectory in the xy plane, and so just be aware that if the particle didn't have any velocity parallel to the magnetic field, then it would just be doing circles in a plane, and the magnetic field would be perpendicular to that plane. Okay, but in this case, in the general case, the particle is going to go in a helix, which means that if I choose the xy plane to be the plane in which the particle is moving at this instantaneously, then the magnetic field is not going to be perpendicular to that plane, right? It'll be at some angle to that plane. Now, what I'm really trying to calculate here is, let's say a particle is going in the xy plane instantaneously as it moves in a helix. And I'm going to assume that the particle is highly relativistic. Okay, that's the limit I'm interested in, which means that the radiation from the particle is going to be beamed in the forward direction, right? We showed that in the previous chapter when we studied the aberration of light, which means that as the particle is moving, it's almost as if the particle has a flashlight on it, and then as the particle curves, its radiation keeps getting beamed in different directions. So just think of a particle having something like a directed flashlight on it. So what you really want to calculate is this whole quantity you're going to calculate is completely dependent on how that narrow beam of the particle cuts across the observer as the particle moves on a curved trajectory, right? So I'm going to choose the observer to be in the xz plane here. Okay, and that's the n hat, which is the position vector to the observer, and I'm just going to say that n hat makes an angle theta with the x-axis. So remember, the particle trajectory is in the xy plane instantaneously at this instant, and I'm choosing the observer to be in the XZ plane, such that if you think of the particle emitting a narrow beam in the forward direction, as the particle is curving, that beam is going to sweep by an observer in the XZ plane. And I want to calculate the profile as the beam sweeps by, right? As the time profile of that beam, the Fourier transform of the time profile is what I'm after. That's what I'm trying to calculate here, is the Fourier transform of the time profile of the beam as the particle sweeps by you. Okay, so that's what I'm after. So I put the observer in the XZ plane. Okay, so let's say the particle velocity is v, the radius of curvature is a, v t prime by a is the angle here of the particle, and so we can have some definitions here. We are going to basically have two more unit vectors. So one unit vector I'm calling epsilon perpendicular, and I call it perpendicular because it's perpendicular to the magnetic field in this case. So you can already guess that the magnetic field in this case lies in the XZ plane, right? The particle is making a helical motion, so the magnetic field should be in the XZ plane if the particle motion is in the XY plane in this geometry. So E perpendicular is just the emission perpendicular to the magnetic field. And so we're going to form a new right-handed set where I have N, I have E perpendicular as two orthogonal vectors. So I can complete that set with an epsilon parallel, which is N cross epsilon perpendicular. So I have a right-handed set in N epsilon perpendicular and epsilon parallel. Okay, so that's sort of the geometry. So just keep this geometry in mind. If you want during the derivation, just go back in the video so you can have this geometry in your mind. Okay, so let's see how to evaluate these expressions here. So in our particular case for synchrotron emission, I can now evaluate n cross beta. Okay, so n cross beta. So I can write out beta, which is just the velocity vector. And the velocity vector has two components, one along the x-axis and the other along the y-axis, right? And y being the E perpendicular axis. Okay, so I can write the velocity vector as a component along the epsilon perpendicular axis. And that's the sign of the angle. So that's the component along the perpendicular axis, and a component along the x-axis, which will be the cosine of the same angle, basically. So that's n cross beta. So I can write it out now. I know what n cross epsilon perpendicular is. That is minus epsilon parallel. And I'm left with doing n cross x. And so remember that this angle is theta here. So you know how to write n cross x. That's going to be along epsilon perpendicular, but there's going to be a sine theta now because of the cross product. They're not orthogonal. Okay, so we know how I can take a cross product with n again. So remember, n epsilon perpendicular and epsilon parallel form a right-handed set. So these cross products are easily taken. So n cross beta is this expression here. So I'll let you to go through the algebra and check this. Okay, so we just need to do one more thing now, which is the quantity in the exponent. So we can write that out, t prime minus n dot r naught by c. Again, that can be written out. R naught is just the position vector of the particle, right? And the particle is just doing instantaneously, it is going along the circumference of a circle. And again, in reality, it's going in a helix, but it's the instantaneous velocity that matters here because we are really going to see a pulse of radiation from this particular instant when the particle is just moving in your direction, close to your direction, right? That's when we're going to see a pulse of radiation from the particle. So we're really trying to calculate the circular trajectory in that instant of the particle, right? So the particle in this instant is going in a circular trajectory in the XY plane. Okay, so that's again easy to write. You know how to write the equation of a charge moving in a circle. It's just x and y in the XY plane, so sine and cosine. So you know how to write that. And n dot of x and then n dot of y is what you need to figure out. And n is in the xz plane, so n dot of y goes to 0. So you're only left with n dot of x. There's a cosine theta there in n dot of x, because theta is the angle between the two vectors. Okay, so you basically get this complicated looking expression, and it comes down to us being able to integrate this expression, right? I mean, that's the challenge now. Can we integrate this expression? So it turns out that in the general case, again, you can't get a closed form solution. But in the particular case of a highly relativistic charge, you can make some approximations and cast them in the form of elementary functions. So how do you do that? Now, the way you do it is actually, well, if you have a look at this, there's basically the perpendicular component and the parallel component. So you can do these things differently, one by one. So I can take the energy emitted perpendicular to the field and then parallel to the field, and then those are the two expressions. So those are basically the Poynting fluxes, if you will, on the two orthogonal axes. Now it comes down to solving this integral. Again, there's no closed form solution, but for a highly relativistic charge, most of the contribution is going to come from close to t prime equal to 0, right? I mean, that's t prime equal to 0 is when you will see that pulse from the charge. So it's a tiny part of the trajectory of the charge around t prime equal to 0 where you actually see the emission from the charge. So you can make some expansions around t prime equal to 0, and we are just going to Taylor expand around t prime equal to 0. Now, you have to be careful when you Taylor expand something which is in the exponent and something which is outside the exponent, right? So here, for the sign, I can do a first order Taylor expansion, and that's fine. But over here, if the sign appears inside the exponent, then I have to be careful in actually doing a higher order Taylor expansion here, because you just introduce a huge error by expanding the exponent to first order. There's less error you introduce in expanding something here to first order as opposed to the exponent. So what we're going to do is we're going to expand the exponent to a higher order, and then we'll just expand this to Vt by A. Okay, so let's Taylor expand the exponent here. So I have a cos theta, I have a sin Vt prime by A. Cos theta is just expanded to second order. It's 1 minus theta squared by 2. Now sine only has a first order and a third order in its expansion, right? It's not like cosine because it's not an even function like cosine. So I'm just going to take the linear term and the cubic term, okay, for the sine. Okay, so the rest is just a bunch of algebra where I've set beta almost equal to 1, where I've set 1 minus beta equal to 1 by 2 gamma square. I mean, all of this is true for the ultra relativistic case, and I've dropped and I've set 1 minus theta square by 2 almost equal to 1. Basically, this is the higher order term in the product here, right? So you make a very small error in this higher order term by setting this equal to 1. Yeah, so you basically go through the motions there, and then the algebra there, and then you get some expression that looks like this. So you get something that is linear in t and then cubic in t. And yeah, so things outside the exponent, well, you just Taylor expand this to first order. So you get these two expressions here for the perpendicular and the parallel component. So you get an integral that has in the exponent a linear and a cubic term. So it's a very complicated integral, of course. It's not a simple Fourier transform because you have this cubic term here. And yeah, so there's an odd function here for the perpendicular component, and it's an even function outside the exponent for the, is basically 1 for the parallel component. And again, a small notation here. So theta of gamma is 1 plus gamma square theta square. So this is just a shorthand. Now, it turns out that this is in the form of elementary functions. And again, I don't expect you to know all of this. In reality, when you encounter something like this, you're going to open a handbook of mathematical functions or something to try to find the closest elementary function where you can cast your integral into. And it turns out that these are the modified Bessel functions. Now it's of fractional order. So it's k, which is the function to the fractional order 2/3 and 1/3. Okay, so again, I don't expect you to, in real time be able to derive all of this, but I just want you to show you the steps involved and where all of these results are coming from. So again, in class, we are going to do a simpler intuitive derivation for these quantities. But this is the rigorous, analytical derivation, which is, is highly accurate. So what you'll do in class is going to be an approximate thing, uh, uh, but much simpler and gives you more insight. So I want to do that in class because it gives you more insight. Okay, now what does the emission actually look like? So I can, if I just want to know what the spectrum is, I can integrate over the solid angle. Okay, so there are thetas here, so you have to go through the integrations with solid angle. Again, those are integrations of these elementary functions, because the solid angle is inside the argument of the function in the form of theta r. So again, the integrals of these things over all solid angles are not going to be elementary functions, so they're just called f of x and g of x. So f of x is defined here, g of x is defined here. And you basically get this kind of spectrum, again parallel and then perpendicular to the magnetic field. So what's happening if you zoom out of the geometry? So if you imagine that the particle is going in a helix, which I've drawn here, and the magnetic field is vertical, then because of aberration, if the pitch angle of the particle is alpha, then you're basically going to get radiation on the surface of a cone of opening angle alpha, right? So as the particle is moving in the helix, it's going to emit along this rim of the cone, and the spectrum of the emission is basically going to be given by these functions. So now I'll show you some, in class I'm going to show you some numerically computed spectra, or maybe I'll put it in the next video. I'll just go through a numerical integration to calculate the spectra. But suffice it to say that f of x and g of x both are functions which start off at 0 as x equal to 0. So remember that x is basically a scaled frequency. Okay, so this is the spectrum. X is the scaled frequency, and it's omega, which is the angular frequency, divided by some scale factor, and you will get an intuition for what this is. I'm going to call it omega c, but we're going to do some problems in class where you'll see that this is actually the Doppler boosted cyclotron frequency. So you can kind of see it here. QB by MC is the cyclotron frequency, right? And so there's a gamma square in front of it. So it's some kind of a Doppler boosted cyclotron frequency. So it's a cyclotron frequency times a large factor, which is gamma square. So some kind of a Doppler boost to the cyclotron frequency is the way to think about it. So anyhow, x is the scaled frequency, and these functions f of x and g of x both start off at very low values as x equal to 0. So they approach 0 as x goes to 0, and then they have a peak around x of the order unity, and then they exponentially fall off for large values of x. So the main idea here being that most of the emission is concentrated in frequency around x of the order unity, which is to say that most of the emission comes out at this Doppler boosted frequency, where omega is almost of the order of omega c. So at very low frequencies, you get very little emission, and very high frequencies, you get almost no emission. So what we are going to do in class is to assume that the emission is almost like a delta function at that particular frequency. And then we're going to go through we're going to show that it's concentrated, and then we're going to go through the derivation, which is much more intuitive. But if you actually want the rigorous correct answer, these are the steps to follow, which I have just followed. So yeah, so that's the derivation of the spectrum of synchrotron emission, and the polarization, of course. So the polarization is, there is a component of it that is perpendicular to the magnetic field, and there's a component which is parallel to the magnetic field. And by parallel, I mean as seen by the observer, right? So if you're thinking of an astrophysical source, and so you can only measure things in the plane of the sky. So there is a component which is perpendicular to the field in the plane of the sky and parallel to the field in the plane of the sky. Now it turns out that both f and g of x have this form where they rise and then they exponentially fall, but g doesn't reach the same peak as f, right? So f of x plus g of x is, and they're both positive, by the way, they're both positive definite. So the perpendicular component is actually stronger. There's more energy that goes in the perpendicular component. The parallel component has a negative sign here, so there's less energy in the parallel component. So the final result is that synchrotron emission is largely polarized, but it has a linear polarization, and it is polarized perpendicular to the magnetic field. So in the plane of the sky, if the magnetic field is along the meridian, then the emission is going to be polarized perpendicular to it. So let's say in the perpendicular to the meridian. So in the direction of so let's say left, right, as you would see in the sky. Yeah, so that's the spectrum and polarization of synchrotron emission. Again, we'll do all of this in a more intuitive way in class. I'm just going to give you a set of increasingly complex problems such that when you solve them one by one, you will reach, you know, sort of a similar result for the spectrum and the emitted power. And so you will get a better intuition, but this is the rigorous way to do it.